So this is actually not about compiling to machine language. It is about Lisp to Lisp transformation, and it's about the story that makes this really unique to Lisp. So perfect hash is a hash function that, given distinct inputs, returns definitely distinct outputs. So it's a hash function that guarantees that its outputs do not collide. And this is further sometimes described as a perfect hash, which uses some number of bits that's minimally necessary, but you may map into a not dense range. And a minimal perfect hash maps exactly into 0 to n-1 for n keys. I've made a slight error on the slide in the naming of my argument to my pseudocode, doesn't matter. So how do you get one of these? But you don't build it, you buy it. So some libraries generate minimal perfect hash functions, and they operate typically in one of two ways. You hand it keys and it hands you back some instance of a thing. You can then call that thing. Maybe this is Python syntax, whatever, doesn't really matter. Or the offline version is you run a program and it gives you back a C program. You compile the C program, you call that C program with an API. This is obviously not as useful. I think gperf works like that. Gperf is a GNU thingy. So how do they generate the perfect hash? And there is my answer. And then there's like what they really do. But again, we're not going to care about how they generate a perfect hash. So here's some C code. And before you throw tomatoes and say, Doug, this is a C function. Well, so yes, but what you're going to find is interesting about the C function is it's not a C function, it's a Lisp function. The tables, watch this, I'm going to flip between the two screens. The tables are identical. The shift operators are identical. Literally everything is identical, except all I did is define some macros that make this look like the C function in every possible way, right? So all we have to worry about is, does overflow happen if you're computing in C, and these are all in uint32 variables, then it does what you mean. So the algorithm has a certain expectation, which is that it knows shifting bits out to the left loses bits off to the left, and shifting bits off to the right loses bits, and that's fine. We can emulate that in Lisp easily enough. I didn't throw in the masking steps that would be necessary to make that happen. So let's say we have a couple of structure types. Structures are named by symbols. Symbols have names that are strings. In SBCL anyway, strings have deterministic hashes. And this may be the case in other Lisps. I suspect it is. Nobody really wants random hashes of strings. So what this in fact means is that each of these structure types has a deterministic hash. And it's not a thing that you have to compute with any kind of complicated function, because you just, whatever it is, you store it in the structure type. You store it in some structure metadata. So for any instance of thing, literally getting its hash is one instruction. Maybe it's two instructions. Load the thing's metadata, and then load a word from the metadata. So where are we with this? This is the last slide. This looks like a lot of code, but it's insanely simple code. So we have a structure instance, which is called X. We're going to get the metadata, which is class of X. I'm not quite using Common Lisp in exactly the right way. I'm not really going to call class of. I'm going to call something that maybe gets me something that really indicates the primitive type of this object that may or may not be a class. In PCL or class implementation, you call it the wrapper, which is really a thing that points to a class. And the reason you do that is you say, X is an instance of a certain type that it is right now, and then that might point to its class. You then ask if it's a structure. In SBCL, this is a 1-bit test. You get a bit out of the structure, or a couple bits out of the structure. You hash it perfectly where it says perfectly hash. You check that it comes back with a small number, because if it didn't, you fed garbage into the hash function. That's fine, it just gives you garbage back. You reference an array of constants indexed by that hash. You say, do I match? And then if yes, you go and do something which we can assume dispatches an O of 1 time. So an integer switch, we're going to call that. And what you can do is the same thing with symbols. So if the things weren't instances but were symbols, they also have constant hashes that are deterministic, and the same technique applies. So we can do something really unique in Lisp that I don't think you could do this in any other language, is just-in-time compile perfectly dispatched case statements in O of 1 time, dispatch in O of 1 time. And there's 5 minutes.
Nicely done.